Okay, 2 o'clock. Welcome back to your favorite class. Rawr. Announcements, graded homework number 1. So you should have gotten an email back from me about your homework and the grade associated. So make sure to check Canvas to see that grade and make sure it's accurate with what I sort of responded with in my email. Generally a pretty good job. Somewhat easy material to start with. I think a lot of people have done vector mechanics and vector math before, so kind of off to a good start. Like to get off on the right foot. So generally good things, what I saw. Okay. You've got homework number 2 coming. I wanted to get it done yesterday, but just stuff came up. So I'll have it posted tonight. It'll be due next Thursday. It's going to be on 2D particle equilibrium, which is kind of the stuff we're doing right now, and also 3D particle equilibrium, which we're going to start on tomorrow and work through some of next week. All right, so that's coming. And your first exam for the class is next Friday, right before Christmas break. So get ready. I'll probably hold a review session Thursday night. Information on that to come a little bit later. I like to host review sessions. And it'll be centered probably around a set of review problems that I send out probably later this week. Okay, so look for that, more information to come. Any questions on anything we got going on? How do I format my tests? 3 problems, all workout problems. I haven't decided what they are yet, so I haven't written the test yet. The way we're going to do tests in this class is we'll do it virtually during the class time. So come to the virtual lecture, turn your camera on, point it towards your workspace. There'll be more details and instructions to come, but basically the idea is, point your camera at your workspace, do your work on a piece of paper and scan it or take a picture of it and send it to me just like you turn in homework before the hour is over. That's kind of how the test works. Right, so you'll be doing that virtually, so you can come to the classroom and do that if you want, but most people just do it at home or whatever workspace they want. I will not be here to answer your question. Okay, other questions? More information on the exam and how we take the exam to come. It's going to be open everything, by the way. Open whatever you want. All right. Okay, so today, usually I like to take, when I teach, a couple of days here and there to just kind of like come together in groups and work on practice problems. But obviously, I don't think that's a good idea right now to get in groups of like 3 and work on practice problems. So instead of what I thought we'd do today is I'd kind of put a practice problem up and maybe give you 5 or 10 minutes to work through it, and then we'll work through the solution as a class. So that's what we're going to do today. I have 2 practice problems on 2D equilibrium. So I'll post it up there, and I'll give you guys, 5 to 10 minutes or so to work through it, and then I'll come back on the mic and we can go over the problem. So without further ado, let's just do some statics. Okay, so here's practice problem number 1. We got this sort of system here that's held in equilibrium. And remember what equilibrium means is that this thing is sort of like not moving. And what I'm asking you to do here is determine the tensions in the cables AB and BC necessary to support the 60 kilogram cylinder at point D. So kind of the way you probably want to attack this is look at drawing a free body diagram about that ring at point B and calculating the forces associated using your equilibrium equations. So I'll go ahead and give you till, I got 2:04 on my watch. Let's give you till 2:12 to see what you can come up with here. And you at home, no going to YouTube. Work on the problem. Try it for yourself. I'll be back. I'm gonna walk around and socially distance check your free body diagram. Make them big. Like, here, look at that. Setting up like a whole IT department up here in the front with all these cords and this computer. As a warning, you're going to want to convert that mass of that cylinder into some sort of force somehow. Mass and force are not the same, so think about how we do that. Mass is not a force. Rawr. Okay. I'm going to get this into the OneNote. Okay, a couple more minutes. Anybody got any answers yet? Still working hard and diligently in person. Got some numbers over there? Cool. Okay. Anyone else? Got values. We'll see. Right, so we're asking for what is the tension in each one of the wires separately. So the tension in AB is going to be different from the tension in BC, which will be different from the tension in BD. Okay, give you maybe another 30 seconds to kind of wrap it up, and then I'll work through it. Okay, so let's go over it. We want to determine the tension in cables BA and BC necessary to support this particular cylinder. All right, so this cylinder down here, we're told weighs 60 kilograms, and we're going to want to convert that mass into a weight. And remember, mass and weight are not the same things. Mass is a scalar value. Weight is a force with a certain direction. All right, so we will do that in just a second. And the best way to analyze this is to consider point B, which is kind of this junction where all of these sort of forces are coming together. And think of point B as like our particle in this particular problem. And we're going to say that the forces that are acting on point B are keeping it in equilibrium. So if this thing is all stationary and holding steady, that the sum of the forces at that particular point at point B is going to be equal to 0. So we have some of the forces in x equals 0, some of the forces in y equals 0. So what we want to do then is we want to isolate point B by drawing a free body diagram. And remember that we sort of label this as like our space diagram. And we want to convert that space diagram into a free body diagram. And the way that we do that is we're isolating this particular guy by sort of like drawing this isolation circle around it and then accounting for all of the things that we're like cutting through in our free body diagram. So we can see here that if we're sort of isolating this particular piece, that we're cutting through this tension, this particular wire here at BC, we're cutting through the wire at AB, and we're cutting through the wire here at BD as well. So let's go ahead and investigate this particular point B, and let's do our free body diagram. So when we cut through each one of these particular wires, there's a tension or a force associated with each one of these wires that we can draw. So the first one's pretty obvious, and that is just this tension downwards, which is the tension in wire BD. So you might want to label this as like TBD, to be determined. Just kidding. Or maybe you'll just label this as the weight of this particular cylinder. All right. So we'll just leave that there for now. We also want to consider what's going on at rope BD. So we can make ourselves a arrow to represent the tension in BD. So maybe we'll label this as, TBC. You may want to label this as like the magnitude of FBC. It's all kind of equivalent at this point. And then lastly, you've got this tension that's kind of pointing backwards here, which is the tension between A and B. So here we got TAB. And let's be clear about some of the extra information that we know. Like we know that this angle BC is 45 degrees with the horizontal, so that might be useful information to know. And we also know that this tension AB is kind of forming like a 3, 4, 5 triangle with the X and Y axis. So that's additional information that we have here in this particular problem given to us, is that this is making like a 3, 4, 5 triangle. So there's a couple pieces of, there's a couple ways that we can sort of handle that 3, 4, 5 angle. But the best way and the way that I think is most useful is to just assign sort of this angle here that exists as the angle, let's call it phi, and we can just solve for phi directly. So let's bang out some additional information that we just know about this particular free body diagram. But I would say that this free body diagram here is nice and complete, and it gives you all the information that you sort of have for the problem. You got this angle phi, you've got the 45-degree angle for TBC, and we're kind of on our way. So one last thing that we kind of need to know here is what is weight? Okay. And sort of if you've taken any elementary physics class at this point, you should know that in this particular situation, since the weight is pointing fully downwards, the weight is just going to be mg, the mass of the cylinder times the acceleration of gravity. The mass we're told is 60 kilograms. So here we have 60 kilograms times the acceleration of gravity in metric units, 9.81 meters per second squared. So we work through this and we get the weight of our cylinder is going to be 589 newtons. Okay, so that's a useful piece of information to know. And so we can go with that straight away. Now we know that if our particle is in equilibrium, we have sort of a mathematical definition for what that means. So if in equilibrium, then the sum of our forces in x and sum of our forces in y equal to 0. So in equilibrium, sum of the forces in x equals 0, and sum of the forces in y equals 0. So we can sort of investigate each one of these directions straight away. Before we do that, we might want to calculate quickly what that angle phi is. So we'll make a little side note here. At that angle phi, if we go back up to our picture, is the tangent inverse of 3 over 4, or if you want the sine function, you could do sine 3 on 5, or if you want cosine, you could do cosine 4 on 5. All going to get you the same thing. It's tangent inverse of 3 on 4. And we'll find that this angle phi is 36.9 degrees. It's warmer than that outside right now. Dang, it's so nice out there right now. Okay, so now we're ready to go. Let's do some of the forces in x equals 0. All right, so let's investigate what we've got going on here. Since this weight is like fully in the y direction, we don't have any contribution of that like weight in the x direction. All we really have to consider is the tension in BC, specifically the component of that tension in the x direction, and similarly the component of the tension AB in the x direction. So we can see that we'll resolve TBC into the x direction through cosine 45, and we'll resolve TAB into x through what is like the negative cosine of this angle phi. So let's go ahead and do that. So if we do the sum of the forces in the x, you're going to have something like tension BC times cosine 45 minus tension AB, since we're kind of pointed in the negative x direction, times the sine of my angle phi, which is 36.9 degrees. This is equal to 0. All right. So if we sort of solve here, we're going to get some relationship between the tension in BC and the tension in AB. And you can like work your way down and solve for either one of these variables if you want. I solved for TBC. So here, TBC is going to be 1.13 times TAB. Okay, so we'll call this star for now, and we'll come back to that. That's kind of like one relationship that we generally need for this particular problem. So here we still have two unknowns in one equation, so we got to sort of whittle this down a little bit further. And we're going to do that by introducing one more equation, which is just that the sum of the forces in the y direction equals 0. Okay. Here now we have contributions from the two tensions, but also have to consider the weight of the cylinder as well. All right, so if we look at this guy, here we've got TAB, and we're going to resolve the y component of this with positive sine 36.9. Okay, so if we just peek our heads up just for a second at this free body diagram, we're resolving this particular force, the y component of that guy, through the sine of this angle phi, which is 36.9. And note that it's in like the positive y direction. Okay, and then we're going to add to that the contribution from BC. So also in the positive y direction is TBC, sine of 45 degrees. And don't forget to subtract the weight, which is fully in like the negative y direction. All this together equal to 0 because we're in equilibrium. So let's just go ahead and plug in information now, and we'll utilize sort of this start equation here to plug in for TBC as we go through. All right. So then we get TAB times sine of 36.9, which you can do this yourself, is 0.60. And that sort of makes sense. It's 3 on 5. Plus TBC. Okay, so we're going to plug in for TBC here from above, that start equation, which is just 1.13 times TAB multiplied by my sine 45. Or if you want to put in some actual values here, sine 45 is root 2 on 2, or 0.707. Minus my weight, which I calculated before, 589 newtons. It's all equal to 0. So here now I've whittled it down to one equation, one unknown. So you can just use algebra to solve here and get that the tension in AB, once you sort of make your way through the algebra here, 421 newtons. So there's your answer for the tension AB. Okay. So that's kind of one component of this problem. We still need to solve for like the tension in the other rope, tension in rope BC. So we can plug this back into that start equation above. And we'll find that T BC is equal to 1.13 times that TAB, which is 421 newtons. So this will give you that TBC is 476 newtons. Newton. All right, so there you go. So here we just kind of assigned what is the tension in each one of these ropes, what is the direction associated, looking at what contributions they give in like the x and the y directions, and then summing the forces and setting them equal to 0, because we know we have this static equilibrium case, right? So it's like we're getting these two equations, two unknowns, and working our way through that. Okay. Any questions on this? In-person folk or online folk? Okay. Let's go through another example. We're leveling up, level 2. All right. This is going to look very similar. You're going to have a very similar procedure here, except you're kind of just solving for different variables. So let's take a look at this guy. All right. So here's our next example. We've got a 200 kilogram crate. Again, this is a mass suspended using these particular ropes or this particular setup. Each rope can withstand a maximum of 10 kilonewtons before it breaks. Ooh, complicated. If AB always remains horizontal, you kind of see that in the picture there, determine the smallest angle theta, which the crate can be suspended before one of the ropes break. Hot dang, complicated. All right, so we'll give you maybe another 10 minutes here. Come back at 2:35 and I'll make my way through it. So give it a go. Give it your best effort. Again, here we've got this like equilibrium situation. So carry your variables through and see if you can go ahead and solve for it. And if you're watching this on YouTube, you can fast forward. Once you've figured out the answer, that is, on your own. It's one of the benefits of like pre-recording the lectures is I can just say, okay, go ahead and pause now and work your way through it. And then wait like 5 seconds in real time and then say, okay, I hope you got the answer. Let's go. Exactly. Get done with a 50-minute lecture in 10 minutes. Again, your strategy is probably going to involve free body diagram of this particular point here. Remember, you're going to have to convert this from mass to weight. So keep that in mind also. All I can really see. Like see the map. Never look at the again after this class. Sure. So if you haven't uncovered this yet, there's a little wrinkle in this problem here where you sort of have to determine which one of these cables is the one that's going to snap at 10 kilonewtons. That's kind of a tricky part of this problem. Maybe take a little time to think about how to figure that out, or how you might determine which one of these cables is going to snap first with that 10 kilonewton restriction. You might be able to intuit it just by the picture, but proving it with math is also helpful. All right, I'll give you maybe 2 more minutes, and then we'll give it a go. Okay, let's give this guy a go here. So let's be a little bit more clear about what the question is asking. I think it might help to maybe break this down a little bit more and think about what's going on. So the question is, each rope can withstand a maximum force of 10 kilonewtons before it breaks. If AB always remains horizontal, we want to find the smallest angle of theta, which we can suspend this before one of the ropes breaks. So kind of in math language, what we're actually looking for here, if we want to break this down, is what value of theta, so that my tension in AC and tension in AB and tension in AD are all less than or equal to 10 kilonewtons. That's what you want. You want all of them less than or equal to 10 kilonewtons. All right. So here's our free body diagram. I think pretty straightforward at this point. Kind of got some good practice with this now. Don't need to beat this to death. I want to make sure that we do get the right angle of theta in here. So your complementary angles, or your equivalent angles, this angle of theta is going to be the same as this angle here of theta. So make sure that you just got the right sort of angle in there. And so if we draw this into our free body diagram, your angle of theta is here. So let's make sure that we get that correct straight away. You don't want your sines and cosines flipped. You're going to be in trouble, rawr, etc. Okay, So let's first examine what's going on in this like rope here. I think it's pretty obvious what's happening here. So let's just go through that really quick. So obviously the tension in rope AD is just going to be equal to the weight of this particular crate, which here is just the mass times the acceleration of gravity. All right. So the mass of the crate given in the problem, 200 kilograms. All right, multiply this by the acceleration of gravity, metric, 9.81 meters per second squared. So we work this out, we're going to get 1962 newtons. 1962, the year I was born. Just kidding. 1962 newtons. All right, and notice there's like no dependence on theta for this particular value. The tension in rope AD is always going to be that value regardless of theta. So does not depend on theta. So this tension AD is going to be less than or equal to 10 kilonewtons always. So for all theta. So we don't got to worry about that guy, all right? There's no way that that guy is going to be our limiting factor, all right? I think you might be able to sort of see that or understand that straight away, but nice to actually put some like math to it, all right? But this is still a useful value for us to know, this 1962 newtons. Okay. So let's move forward and we'll sort of assume equilibrium is happening here. And I'm going to establish a relationship between the tensions in rope AC and AB. And the reason I want to do that is I want to know generally which one of those is going to be under greater tension. So let's put that into words. So to determine which rope is in greatest tension, we'll use sum of the forces x equals 0. And I'll show you what I mean. All right, so let's do that. Let's enforce one of our equilibrium equations. Sum of the forces x equal to 0. Okay. If we do that here, our tension of rope AB, which is this horizontal force, is always going to be in the positive x direction. So we don't have to modify it by any angle. It is just TAB. So if we kind of go back up to our free body diagram here, it's in this positive x direction. We're not modifying by any angular value. So we just have this TAB in positive x. All right. For AC, it's kind of pointing to the left. So the negative x direction, modifying by cosine of the angle theta. And theta we don't actually know. So here we have minus TAC times cosine theta. And these are the only forces that we have in the x direction. Since the weight of the crate is fully in the y direction, it's not included in the x force summation. So here we are in this particular situation. You can solve this for either one of the variables. I here like to actually solve for TAC, which is a little bit strange, but I'll talk about it why in just a second. You'll see here this is going to be TAB divided by cosine of theta. And here's a relationship that we establish, and one that, you know, just looks like a mathematical expression on the surface. But if you actually think about the range of the values of theta that you could possibly see in this problem, it helps us to understand which one of these two tensions is going to be greater, okay? And so we can make a little side note here and say, look at this particular guy. Say that since sort of the range of values for theta is, you know, 0 to 90 degrees realistically for this problem, we'll say since cosine theta is always less than or equal to 1, then TAC will always be greater than TAB. Okay? Hopefully we see that mathematically. That means that the rope that is governing failure in this problem is the rope AC. So AC governs failure. and will be first to reach 10 kilonewtons. Okay, so some mathematical justification there. Okay, so what that means is let's set TAC as 10 kilonewtons, because that's when this is going to fail, and that's kind of our failure condition. So when that TAC reaches 10 kilonewtons, we're going to fail. Okay. All right. Now let's do our sum of the forces in the Y. All right. So if we sum the forces in the Y, we have that TAC, and here we're modifying TAC by the sine of theta, and it's in the positive Y. So TAC, sine theta. Remember, the rope AB is always horizontal, so we're not considering it in the Y summation here. The only thing we have to consider is the weight of this crate. Minus W, this equal to 0. Since we know that TAC is sort of the limiting factor here, and we're setting it to 10 kilonewtons, we can actually just go ahead and solve this straight away. So TAC, we're going to say this fails when this reaches 10 kilonewtons times the sine of theta minus my weight, which I solved for before, 1962 newtons, all equal to 0. And sort of make your way through this and find that theta will be the inverse sine of 1962 over 10,000. Making sure that your sort of units match. Okay, 10 kilonewtons is 10,000 newtons. So 1962 newtons over 10,000 newtons. This is going to be my expression that's dictating what theta is. And we can solve here and determine that theta is 11.3 degrees. And that is the answer for this problem. We can check the tension in the other rope just to make sure that it is indeed less than 10 kilonewtons. So let's check. What is the tension in AB? And we can do that with our expression that we had previously, which is here. Can rearrange this. And see that TAB, if TAC is 10 kilonewtons, multiplied by the cosine of 11.3. And you'll see here that, yes, indeed, we're going to be less than 10 kilonewtons, some percentage of that. Here it's actually 9.8. Okay, so this is a good check for us. All right, so that'll do it for this problem, and that'll do it for today's lecture. Just a couple of example problems. I like to do this from time to time. Hopefully you like this style. That's going to be it for today, and that's going to be it for our discussion on 2D equilibrium. So look for a homework posted tonight. You'll see some 2D equilibrium problems, and we'll see you again tomorrow for new material.